So quarks are never alone, a little bit like sailors on leave in a military and in a navy. They're never allowed to go ashore alone. They always go in pairs or in triplets. And quarks are never alone. They appear in clusters. And the simplest questions we want to ask is what clusters are allowed and stable or semi-stable. And thus our topic can be rephrased in somewhat, I'm not sure I'd be allowed to display this transparency in America because of all the craziness. So it's the social life of quarks. Who with whom, for how long? Is it a passing fling, or is it till death us do part? Is it a stable relationship, or is it just, you know? Okay, so we know that quarks are fundamental building. All quarks are equal, but heavy quarks are more equal than others. And I will explain what exactly is meant by this statement. And in recent years, we witnessed a large number of unusual combinations of quarks, including heavy quarks, and most conspicuously, fairly recently, the LHCb collaboration at CERN has discovered a tetraquark with two charm quarks, not charm and anti-charm, but two charms. So, and two light antiquarks. Theoretical work has led us to a fairly firm prediction that there exists at least one tetraquark with two B quarks which cannot decay via strong interactions. So it's stable and can only decay weakly. And there is a large number of very interesting hadronic molecules which are analogs of the deuteron, most importantly pentaquarks. So all these things are like new layers of a periodic table, quite interesting, and some of them quite unexpected. So these are the, is there a laser pointer somewhere? Yeah. So these are the layers of matter, and starting from crystal, molecule, atom, nucleus, proton with quarks and leptons. And we will be focusing on that region, but proton is a very straightforward combination of three quarks, and we want to ask what are the combinations. And another point worth keeping in mind is that the scale of the masses of quarks spans a very large number of orders of magnitude, from the top quark, which is more than 100 GeV, down to up and down quarks, which are on the order of 10 to the minus 3 GeV, so roughly 5 orders of magnitude. And people who have pioneered this field were Mary Gell-Mann, Yuval Ne'eman, and then Gell-Mann and Zweig, who realized that you could understand all hadrons by assuming that they are built in fact all particles are built from quarks. A proton is built from two U quarks and one D quark. A neutron is built from two D quarks and a U quark, and the arrows here denote the spin. And mesons are built from a quark and an antiquark. The only allowed physical objects are such that they carry no net quantum number of color. Technically, in the language of group theory, that these things are singlets under the color group. Now, QCD tells us that the potential between heavy quarks can be approximated fairly well by a combination of two terms. One is a confining term, a potential which grows linearly with the distance, and the other is Coulomb-like, with the alpha of QED replaced by the strong coupling constant alpha S. Excuse me, my phone should have been silenced, and I didn't do that in time. So, now, this has some dramatic consequences, and some of the things I will be telling you result from this region where QCD at small distances is dominated by the Coulomb behavior. This is the potential that we know, and as a result, these beautiful animations are a result of lattice gauge theory calculations done by people in Adelaide in Australia. So you can actually see the chromoelectric flux tube between a quark and an antiquark, and if you take three quarks, you see as you take them apart from each other, you see a Y shape forming of the flux in between quarks in a baryon. Now, this has some really dramatic consequences, because if you take a heavy quark and a heavy antiquark and you pull them apart, the energy inside the flux tube grows basically without limit in a classical theory or semi-classical theory, but in quantum theory, at some point, you have so much energy stored in the flux tube that you can create another quark-antiquark pair from the vacuum, and then the string breaks. And the remarkable thing is that people managed to show how this happens in simulations. So this is an actual simulation, and you can see the energy density in the flux tube. As you pull the quarks apart, this central region, the energy density goes to 0 because a pair of quark and antiquark pops up from the vacuum. Okay. So standard hadrons are baryons with 3 quarks and mesons with a quark and an antiquark. And the focus of this talk today is the so-called exotic hadrons, which have 2 quarks and 2 antiquarks, and they are called tetraquarks. Or they have 4 quarks and 1 antiquark, and then they're called pentaquarks. Now, the fact that you could have exotic hadrons purely by quote-unquote kinematic considerations was understood very early on by both Gelman and Zweig in '64. They pointed this out, but that was just a statement in the language of group theory that you can form a singlet from two triplets and 2 anti-triplets, or from 3 triplets, from 4 triplets and 1 anti-triplet, you can form an SU3 singlet. So this doesn't tell you if these things are stable or long-lived and so on. It just tells you that in principle it's possible. But by now, we have robust experimental evidence that such states exist in nature as either stable configurations or configurations which are metastable but with a rather long lifetime. And these are mesons which contain 2 heavy quarks and 2 light antiquarks, or 1 heavy quark, 1 heavy antiquark, and a light quark-antiquark pair, where capital Q refers to bottom or charm, and lowercase q refers to up, down, and strange. Now, you also have baryons, which contain, for example, charm and anti-charm and 3 light quarks. And the 3 key questions about these systems are which additional exotics we should expect, in addition to those that we have already seen. What is the spatial organization of the quarks? Are they organized in subclusters and so on? And how long do they survive? Some, we know, survive forever within strong interactions. Others survive abnormally long, and we need to understand how does it work. So I will be explaining the various possibilities. And let me start from the observation of this exotic narrow doubly charmed tetraquark, which was announced by the LHCb collaboration in CERN in almost exactly 3 years ago. This was something they were looking for a very long time. And this is a beautiful tour de force of experimental physics. They observed this object decaying into 2 d mesons and a charged pion, and it's extremely narrow, really, really narrow. Notice this thing, this is energy scale in GeV. This is the threshold, and just a tiny little bit below threshold, you have this peak. And usually, strongly interacting particles are either stable or they have a fairly large width. Now, this one is unusual because its width is on the order of much less than 1 keV, the 1 MeV, and it's just a tiny little bit below the threshold, which makes it possible for it to decay because the final state, this guy, has a final width. And it's almost purely a combination of D0, D star plus. That's the physical state that we observe. Now, here comes really an important distinction between the 2 kinds of such exotic objects. Given 4 quarks, you have 2 basic configurations that you could organize them in. One is you put all the 4 quarks, 2 charm quarks, an anti-U and an anti-D, you put them inside 1 confinement volume, such that every quark sees the color charges of all the other 3. That's the so-called tightly bound tetraquark. Or, with the same 4 quarks, you organize them in 2 mesons. It's, you know, it's the same 4 quarks. So, in this case, the mesons attract by exchanging light hadrons, just like the proton and the neutron attract each other in a deuteron. But this is something dramatically different. This is something, so this is the analog of a deuteron. Okay, interesting, but not dramatically new. If this exists, this is something completely new, never seen before. And therefore, it's interesting to see what we can tell, what we can say about this object. So people have speculated about the existence of such an object for a very long time. Its quantum numbers are, it has spin 1, positive parity, isospin 0, and the experimentalists, when they released the paper, they made a compilation of the various predictions. This is the experimental number, and these are the various predictions with the error bars, and just by chance, ours is in red. That's where it is. So we did pretty well, just within a few MeV of the exact result. But that's not the important thing. The important thing is what configuration this thing probably is. So once again, going back to Orwell, heavy quarks are more equal than others because they have very little kinetic energy. They're almost static. Their spin-dependent interactions are very small. And in the past, this was a key to predicting accurately masses of various baryons containing big quarks. Now, what this talk is formally a part of a QCD conference, and what we would like to do in principle in QCD is to calculate masses of all hadrons from first principles. The only way I know of doing such a thing until now is heavy-duty numerical calculation. There is no known analytical approach which starts from first principles. So what we are doing here, we are using a phenomenological model which is basically a form of quark model. We identify the effective degrees of freedom and their interactions and extract the parameters from other experiments and then use them to make predictions. And we apply this toolbox to baryons which contain two heavy quarks, which had never been seen until then. And at the same time, it's possible to use the same toolbox to tetraquarks of this new kind, containing two charm quarks or two bottom quarks. Now, there is an interesting parallel between a baryon which contains two charm quarks and a light third quark, and a tetraquark which contains the same two charm quarks and a pair of light antiquarks. And the color structure is quite similar because two colored antiquarks can combine and form a triplet under color, which for many practical purposes behaves as if it was a light quark. So there is deep similarity between these tetraquarks and baryons. And this is just a quick review of what is known. So in 2014, we made predictions for these heavy baryons. We predicted that the lightest one would have a mass of 3,627 plus minus 12 MeV, and then the experimentalists 3 years later measured 5 MeV away from the prediction. And there are many others which have not yet been seen, but they must exist. And this is something important to stress. Baryons with 2 heavy quarks, such as 2 Cs and a U, are completely not exotic. They are as usual as the proton, and have been seen until recently just because they are difficult to produce, because the cross-section is small. Okay, so the lifetime works okay, and now I want, what is that? Feedback? No. Okay. Hard to imagine something simpler. The mass of such a baryon consists of the masses of the 2 charm quarks, the mass of the light quark, the interaction between the light and the heavy, the interaction between the heavies. Now, the parameters in blue you can extract from other experiments, but the parameters in red, there are no other experiments, because this is the first object in which you have 2 charm quarks. And this was an impediment. Nobody knew how to proceed, because you need to make some educated guess, and nobody knew what that educated guess is. So then, for lack of anything better, we noticed something which had been known for a long time. It's not our observation. It's just a trivial consequence of the color algebra, of the color charges, that the strength of the interaction in perturbation theory between 2 charm quarks is exactly 1/2 of the strength of interaction between charm and anti-charm. And the interaction of charm and anti-charm you know from various mesons. So we made a conjecture that this is true not just in perturbation theory, but it will be true in this non-perturbative system. And at that time, we did not have a good justification for that. Today we understand it. But from here you can immediately proceed, because you can estimate the strength of this interaction once you make this conjecture. And I won't bore you with all the details, but the bookkeeping is simple. These are the masses. This is the strength of the interaction of the charm quarks and the interaction of charm with light, and this is how you get this number. So that worked very well. And then immediately we thought that we will be able to solve a question which was posed many years ago by Bob Jaffe at MIT. Is it possible to have a stable dibaryon with 2 lambda baryons attracting each other such that the mass of this object is below threshold? And it turns out that it doesn't work, even in this case, because indeed it is below masses of 2 lambdas of a doubly charmed baryon and a normal nucleon. However, something unexpected came out of this, namely the observation that with the same theoretical toolbox that led to the accurate prediction of the doubly charmed baryon mass. If you extend this approach to bottom quarks rather than charm quarks, you find that the tetraquark with 2 bottom quarks and 2 light antiquarks is stable under strong interactions. It cannot decay. And my task today, hope I'll be able to accomplish, is to convince you that the physical reason for this is actually quite simple, and once you understand it, it's obvious. And people are looking for this object experimentally, and there are some others which are similar. So how does it work? So this is our paper, which came out, which was submitted very shortly, a week or 2 weeks after the experimental validation of this approach. And then we said 2 things. This is the prediction, which came to 3 MeV. Decay via strong interactions. So how does it work? If you look at a baryon with 2 charm quarks, the 2 charm quarks form a diquark, and because of Fermi statistics, you know that this diquark has to have spin 1. This is actually quite interesting because it's doing quantum mechanics on your fingers. So Fermi-Dirac statistics tells you that a wave function of 2 fermions has to be antisymmetric, and since they form a color singlet with the light quark, and the light quark is a color triplet, these 2 must form a color anti-triplet. But color anti-triplet is antisymmetric in color space, and therefore it must be symmetric in spin in order for the total wave function to be antisymmetric. And now if you go to the analog with the same 2 charm quarks and anti-U, anti-D, the anti-U and anti-D form a composite color triplet with spin 0, because that's the lowest energy configuration of a diquark. This is spin 1, so you immediately predict that the spin and parity of this object is 1+. And this is the quantum numbers. Now, where does the stability come from? The stability comes from that if you have 2 very heavy quarks, they stabilize at small distance, and at small distance the potential is dominated by the Coulomb term, and it's easy to see that the interaction energy of 2 scales like the mass of heavy quarks times alpha s squared. So it's clear that for sufficiently heavy quarks, the interaction energy will be infinite as the mass goes to infinity. So this system must be bound because it's negative binding energy. But no one knew at that time if bottom quarks are heavy enough. And what the experiment did, the experiment which measured the mass of the doubly charmed baryon, is to calibrate, tell us what the coefficient in front is, and then we could proceed by the same bookkeeping as estimate the mass of this tetraquark, and you end up with a mass which is, in our condition, around 200 MeV below threshold. Other people got numbers which are not that large, but everyone by now agrees that this system is stable under strong interactions. It cannot, its mass is well below the mass of two B mesons. So it cannot, there is nothing it can decay to. So what's the trick? The trick is that if you have two B quarks, they stabilize in a very small distance, roughly here, 1/5 of, about 1/5 of a Fermi. Now, in dimensionless units, one inverse Fermi is 200 MeV. 1/5 of a Fermi inverse is 1 GeV. So if you take 1 GeV and you multiply it by alpha S, you get a very large binding energy of 280 MeV. And this is tightly bound, but it cannot disengage from the anti-U and anti-D. Now, if you try to separate it into two mesons, each containing only one B quark, then you lose this binding energy because one B quark is here, another B quark is here, they are far. And so the two B mesons are much heavier than this unusual configuration. Now, something interesting that happens here, and it has some experimental implications. This plot shows the distance from the two meson threshold depending on the mass of the quarks. So two B quarks are deeply below threshold, about 200 MeV. The two charms we know experimentally are essentially at threshold. But if you take one B and one charm, which is experimentally easier to produce and easier to detect, there is a very high probability that this object too will be below threshold. And this is the current focus of the experimental attempts by LHCb. Find it. It will be the first stable multi-quark system, which cannot decay strongly and only decays weakly. There are some very clever people in LHCb who are doing that. So I'm going to skip that. I'm going to skip that. Okay, to summarize. So this is an example of a genuinely new structure, a compact tetraquark, which is so deeply bound by QCD that it cannot decay into two B mesons, B and B star. And there are various ways to look for it and so on. I won't go into that. I'll be happy to discuss privately. This is just a long list of various exotic and non-exotic hadrons which have been discovered by the LHC. And now I want to switch gears. So I told you about this possibility of having a genuinely new structure where you really have four quarks, two antiquarks within one confinement volume. But there is the other extreme where we have these analogs of the neutron. And it's quite remarkable that both kinds exist. So there are several mesons which share some very unusual characteristics. For example, this one called X3872, ZB of two kinds, ZC. Now, what's in common between them? First of all, they are very close to two meson thresholds. Above them, they decay strongly. But on one hand, they have a lot of energy to release when they decay into J psi and 2 pions, CC bar, J psi is CC bar, or upsilon, which is BB bar. So a lot of energy is released. On the other hand, even though so much energy is released, the width is very small, which means they have a very unusually long lifetime. Now, this is really a striking example. You have more than 1 GeV of energy released, yet the width is just about 10 MeV. This is highly unusual. So there has to be some mechanism. Difficult for these objects to decay, because otherwise, if you put inside one volume, 2 B and a B bar and a U and a D bar, there is nothing to stop B and B bar from hadronizing as upsilon and leaving behind a pion, releasing more than 1 GeV of energy, and no way this would have. So we believe that these objects are hadronic molecules, the analogs of the deuteron, where one of them contains a charm quark and an anti-U, and the other contains anti-charm and U. And these are the tightly bound tetraquarks that we talked about before. But these, if they have so much energy, cannot be stable. So the only way you could have a long-lived object is if you have a hadronic molecule, and I want to convince you that this is the case. Another very striking observation, these are experimental numbers. So this object can decay either to 2 mesons, B and B bar, with very little energy release, or to a B anti-B, upsilon and a pion, with releasing 1 GeV of energy or more. Now, we know from Fermi's golden rule that the rate of a process is the matrix element squared times the phase space, the amount of energy, essentially. So you would expect that the process which releases so much energy is dominant, but in fact, it's the other way around. This process in the numerator, which only releases 2 or 3 MeV of energy, is 100 times more likely than this one. And what is the reason? The reason is that the matrix element is just basically the overlap of the wave functions, of the initial wave function of this object Z with either 2 mesons or with upsilon and a pion. Here the overlap is almost perfect, and here it's minuscule. That's why this mode is dominant. So there are several other pieces of experimental evidence in support of this molecular interpretation. First of all, the masses are near thresholds, so it's a weakly bound object, like the neutron is very close, just 2 MeV away from the sum of masses of the proton and the neutron. And if it's a weakly bound state, then it can only be bound in an S wave. So it inherits the quantum numbers of the constituents. So the spin and parity are inherited from the constituents. The width is narrow despite a very large phase space, and the branching ratio to fall apart into 2 mesons is much larger than quarkonium and a light pion. I will skip this one. Now I want to explain, maybe graphically, why it is so. So we had these, I had this plot showing schematically. Okay, so now this example and replace it by anti-charm here. So if this is charm and this is anti-charm and this is a tightly bound state, it cannot be stable because this charm and this anti-charm will couple to form a J-psi, quarkonium, and leave this one behind. But if you have two hadrons, you know, the rough estimate of a radius of a bound state is inversely proportional to the binding energy, to the square root of the binding energy. So if the binding energy is very small, it's a very large object. So here you have this large object with one heavy quark here and one heavy anti-quark here. In order to decay into charm-anti-charm, this C and this anti-C would have to get very close to one another, but the probability of that is very small. So we have a natural suppression mechanism for decay of these hadronic molecules. And now there is a twist in the story. The table I showed you involves only mesons. But then we realized that this mechanism, which makes this object semi-stable but very long-lived, this mechanism can apply not only to two mesons, but to any two hadrons which are sufficiently heavy, so they have little kinetic energy, which is repulsive, and which bind through exchange of pions or things like that. In particular, this can apply to a baryon and a meson. So we wrote down a list of possible candidates. This was PhysRev letters in 2015. And the lightest among these baryon meson bound states is this one, with a baryon called sigma C and a meson called D bar star. This is the lightest one. And so it's easy to predict the masses because the masses have to be very close to threshold. And it's denoted in red here. And it decays into J psi, which is CC bar and a proton. This is the threshold, so we estimated it's just a bit below, maybe 10 MeV below. And we were very lucky because just a few weeks later, this was our paper, just a few weeks later, such a state was discovered experimentally. And ignore the right panel, but the left panel is something called an Argand plot, which shows the complex amplitude, imaginary versus real, where the curve is parameterized by energy. This is an experimental plot, and you can show that if you have a bright Wigner, it's a circle with the line moving counterclockwise, and it's almost a textbook example. And they discovered it's just 12 MeV below threshold. It's very narrow, even though it releases about 400 MeV. And by now, with more refined experimental data, we see something even more interesting. There are three states. There is a hadronic molecule at the threshold of this baryon called sigma C and a spin 0 meson. They see it, and there is only one. And then there are two at the threshold of the same baryon, but a meson called D bar star, which has spin 1. So why is it that here you have only one, and here you have two? The reason is that if I have a if I have a bound state of a particle with spin 1/2, which is the baryon, and a particle with spin 1, which is the meson, they can bind to either spin 1/2 or 3/2, and the interaction is spin dependent. So it introduces a splitting of 17 MeV between them. The picture is completely consistent. And again, if it was quote unquote a tightly bound pentaquark, it would have never be so long-lived, because charm here and the anti-charm here would have coupled to each other, hadronized as J psi meson, and left a proton behind. Okay. So I'm going to skip this, I'm going to skip this.
So how did you make the list of...
How did we make it?
Yeah, how do you know that they are below threshold?
Oh, no, it's the other way around. You assume that if there is attraction between two heavy baryons, there will be a bound state, which will be order of 10 MeV, 10 MeV below threshold. So the list was compiled just by looking that can couple in this way. It's kinematics. Now,
can you show us your first page of the paper of 15, please?
of
15.
this or this?
Yes.
You mean this?
No, the before.
Yes.
Thank you.
So I will give Grisha the talk so you can.
Quick question. Can you return to the experimental picture?
Yes.
No, the other one.
What do you mean? Oh,
The one with the curves.
you mean?
The one with the peaks.
Ah, okay. Yes.
Okay. Don't you say the 444 line seems to be missing, but there is somehow a peak, right?
What is missing? Sorry.
No, you said you put a dotted line at 444.57, but the 44.40 somehow there is something in the experimental curve.
No. This line is this line is just the threshold. The states are denoted by the curves. Okay. So this is an experimental picture taken from an LHCb talk. Okay, so this I'm going to skip, and this I'm going to skip. And now I want to tell you about something that was discovered by LHCb. We're not sure what it is, but it's a resonance which decays into 2J size, CC bar, CC bar. It probably cannot be a molecule because molecules require exchange of light hadrons and these don't couple to charm. It could be an excited state of a tetraquark. We are not sure. It's very interesting. But here I want to spend a few minutes discussing a subtle but very important difference between the two types of exotics, which seem to be have completely different properties, and it was driving me crazy for a very long time. I couldn't understand why it is so. So let me sharpen the apparent paradox. So I told you at the beginning of the talk that the attraction between a heavy quark and a heavy antiquark is twice as much as the attraction between two heavy quarks, just from color algebra. Yet, the exotics, which involve a heavy quark and a heavy antiquark, are all molecules which are very weakly bound. Why then nature doesn't utilize this attraction, which is twice as much as here? Here we know that there is a deeply bound tetraquark. Why not here? Why can't we have a deeply bound tetraquark with two heavy quark and a heavy antiquark? We have twice as much attraction. So something has to give, and once you understand it, it's trivial, but it at least took me a very long time to understand. So the exotics with heavy quark and a heavy antiquark, and those with two heavy quarks are very different. Why can't you use this fact that this interaction is twice as much as this one? You cannot use it because you cannot have it both ways. So if you look at this, okay, let's go back. So let's look at this guy. It has a heavy quark and a heavy antiquark, and a light quark and a light antiquark. If I want to use the fact that this heavy quark and this heavy antiquark attract twice as much as these two heavy quarks, these two attract twice as much only if they form a color singlet. But once they form a color singlet, they stop talking to the light quarks. So you cannot utilize the strong attraction between these two and still keep the others around. Here you have no choice, because even though the attraction between this one and this one is only 1/2 of this, the two heavy quarks cannot exist as a physical state. They form a color anti-triplet, which cannot be an asymptotic state, so they must keep the others around to survive. That's the key to, so my conjecture is that we will not see any deeply bound exotics of this type. If we find exotic hadrons, there will be lightly but weakly bound hadronic molecules. These, if quarks are heavy enough, are very tightly bound. Okay. So let me summarize, because time is, we want to leave some time for questions. So first of all, a narrow, extremely narrow, doubly charmed tetraquark has been discovered by LHCb. Narrow, it means it decays, but decays very, very slowly. On the other hand, doubly exactly were predicted. Probably the most interesting result is that the cousin of this guy, if you replace charm by bottom, it's absolutely stable. And probably if you replace only one charm by bottom, it's still stable, and this is where the experimental focus is. There is a whole zoo of narrow exotics, semi-stable heavy deuterons and hadronic molecules. Many have been seen, and there is many more that we expect. A new animal which is all charm, two charms, two anti-charms, probably an excited tetraquark, but we do not know for sure. There should be an analog with bottom quarks or a mixed, let's say, bottom charm, anti-bottom, anti-charm. Now, the most important lesson, I think, is that these exotic states exist in two basic configurations, both of which are observed experimentally. Hadronic molecule and eventually decay. And in quantum mechanics, an iron rule that if two states have the same quantum numbers and they're close in mass, they will mix inevitably. So it's conceivable and probably even true that some of the exotic states are mixtures of both types of configurations. It's an accident of nature that for charm quarks, the mass is very close to 2 mesons, and it's possible that this object that has been discovered experimentally, this one, is in fact a mixture of a molecule and tightly bound tetraquark. So there is an exciting spectroscopy awaiting discovery, and there is a lot of fun for both experimentalists and theorists. So I should stop here, and thank you very much. If there are questions.
Yeah, thank you very much. Are there more questions?
Yes, please.
Yeah, according to what you said repeatedly, heavy quarks are easier than light quarks. So what makes a description of the C bar difficult or not settled?
Okay. They are easier in the following sense. If you focus on states with only light quarks, to a good approximation, you can ignore their masses, as we know. And then there's one scale in QCD, which is lambda QCD. It's a one-scale theory. Once you introduce quarks with heavy masses, whose masses for charm is about more than 1 GeV, for bottom is 5 GeV, you have another scale in the problem. And then there is a dimensionless parameter, which is the ratio of lambda QCD and the heavy quark mass. For bottom, it's a very small number. And then it becomes, the treatment becomes really fairly simple. And that's why the doubly bottom tetraquark is deeply bound. Charm is just an accident of nature, is somewhere in between. And as a result, we think the doubly charmed tetraquark is just on the threshold, and the state with 4 charm quarks, we have calculated its mass in an approach where we assume it's an excited tetraquark, but we will have to wait for more data before we know if this prediction is in fact correct. I hope that I answer your question.
Yes, sure. But is there any prospect to discover the 4B, BB,
Well, probably it can be done because there are already events with two BB bar pairs. They haven't seen a resonance, but people have observed such objects. Luminosity of LHC is going to go up by such a huge factor in the high luminosity LHC that I think it probably will be possible. I think the challenge will be more in terms of detection and filtering the data than in the cross-section. The cross-section bottleneck is probably okay. Yes?
Just a related question to this one. So you're saying the object is stable in the sense that it doesn't decay through strong interactions. I guess it also means that it's harder to produce. And doesn't that go against just the statement you made, that even if luminosity goes high, you can produce standard PV bar pairs? This one is harder to produce than others.
Absolutely. So, in terms of the two bottlenecks, when you produce an object with two heavy quarks, you have two bottlenecks. One bottleneck is the production cross-section. That we can overcome, we know. But a more difficult is that you need, let's say you have one big quark and another big quark produced from another pair. You need to produce them in such a way that they're close enough to each other to bind and form a hadron. So that means that they have to be close both in ordinary space and in momentum space. Now, you can ask the same question, exactly the same question about doubly heavy baryons, which are not exotic at all. So in 2014, when we wrote this long paper with predictions of masses of doubly charmed baryons, and we went to experimentalists and said, can you guys look for them, please? They said, how do we know that we will not waste the next 3 years looking for something with production times detection probability is far too small and we will see nothing? And they were right, because at that time there were, in the literature, there were predictions of production cross-sections which differed by 2 orders of magnitude from each other. So finally, we noticed something which convinced them. If you look at the diagrams through which such doubly heavy objects are produced, basically the dominant process is gluon-gluon fusion. Gluon-gluon goes to two virtual gluons, which then split into 2 quark-antiquark pairs. And in particular, there is a process where you make a BB bar pair and a CC bar pair, and then they form a B sub C meson. And the same guys, they have observed hundreds of. So this convinced them that the cross-section is large enough. Okay, so I agree with you that it's not obvious that the cross-section, I think that with high Lumi, probably the problems will be different.
Well, deep detection in that case becomes another issue, I guess.
Yeah, but I think that the first thing they will have to see is a doubly heavy baryon, which is easier to produce than a doubly heavy tetraquark. So for example, you would like to see a baryon which has bottom charm and a U quark, or bottom charm and a D quark. And then it's only a little step further, bottom charm and anti-U and anti-D. Okay, because then hadronization is not a very big deal. Okay, did I answer your question?
Yeah, I think it's related to the previous question. So the same small wave function overlap that gives you small decay of the molecules to quarkonia versus the mesons should also suggest that the production ratios should be similarly suppressed.
They are.
Is the data in it, but it's a quantitative question.
A simple answer is that I don't know, because calculating this honestly means doing some very complex Monte Carlos, because what you need to do is, one gluon makes make a charm anti-charm pair, the other gluon makes a bottom anti-bottom pair, and then let's say you want to take a charm from one pair and bottom from the other, and then you need to look at the distribution of this B and C quarks in momentum and ordinary space, and find out how likely it is that they will stick out. But you're absolutely right. That's why it took such a long time to discover these things, because they're not so easy to make. But if you have enough flux and you're patient and clever, as these experimentalists are, eventually you see it. Yes?
Isn't there any lattice calculation of the spectrum for those heavy exotics?
Yes, there is some very good work by I know of at least two groups, one in Slovenia, a very good group, and one in India. And in fact, for the doubly bottom tetraquark, they completely confirm the prediction that these objects are well below threshold. So you can check the box. For bottom charm, it's borderline, because you're really talking about 10 MeV precision. Experimentally, if you have an object which is 10 MeV below threshold, it's absolutely stable from the point of strong interactions. But to get 10 MeV from lattice is not so simple. But for doubly bottom, yes, there is a I know for double bottom there is more than two groups which do that. And this is for the compact objects. For molecules, it's much more difficult, because doing semi-stable objects on the lattice is very tricky. I mean, you cannot use the standard method of extracting a ground state by looking at large distances, because these objects decay eventually. So you have to use all sorts of tricks, Lucier tricks. There are some very clever people who are doing these things, but this is above my level of expertise. We can talk privately if you wish.
I have a question.
Yeah.
When you present a calculation of masses of the exotic states, you're using kind of quark model arguments. But we know a priori that there's a strongly bound state, there's a confinement behind.
Yes.
So it seems like the fact that you were successful in computing those masses, it should tell us about confinement mechanisms which bind those states. Why confinement is such that the results look so simple?
Excellent question, Grisha. This is a question that's been troubling me for many years. The quark model was developed well before QCD. And I think to this day, we do not have a real deep understanding of why it is that the proton can be well approximated, assuming that it consists of just 3 constituent quarks. The closest I have seen is some ideas due to David Kaplan in Seattle, where you can think about constituent quarks as kind of skyrmions in color space. But this is too technical for a colloquium, so we can talk privately.
Yes, so this argument that you put up, that you cannot make a compact state with Q bar, could you use the same argument to say that there cannot be hybrids?
That you cannot,
Hybrids.
what, sorry?
Hybrid
Hybrid state.
state.
What do you mean by that?
Like QQR and some gluon structure. That makes it similar.
I think I think these are 2 different issues. As far as I know, people who talk about hybrids talk about resonances, which can be wide. The question I asked was, why is it that with 2 heavy quarks you get states which are deeply below threshold, but you cannot get states which are deeply below threshold with a quark and an anti-quark? Hybrids, many people worked on that, and I think they probably exist, but they're not stable. So I think it's a different issue.